Today we want to start looking at differential equations. A differential equation is an equation, no big surprise there. It's an equation that involves a function and its derivatives. That's a really hand-wavy definition. It's not a definition, it's just an explanation. A differential equation is an equation involving a function and its derivatives. A differential equation is an equation involving a function and its derivatives. Usually, the function is the unknown. The function is the thing that we are looking for. Usually, it is the function that we are looking for. It's the function that's going to be the solution to the differential equation. What we're doing here is expressing a relationship between a quantity and how that quantity is changing. And that's why our unknown might be a function. We're trying to decide how something is happening, and we observe values for the function and then how the function is changing to try to get an idea of what the function should look like. So it's an equation where the solution is the function, and we're establishing a relationship by looking at the function and its derivatives. So, an example. For example, the rate at which a population grows, the rate at which a population grows is proportional to the size of the population. The rate at which a population grows is proportional to the size of the population. In this case, we could say the size of the population is the function. The rate at which a population grows would be the derivative of that function, the first derivative of the function. And we're saying that these two functions are proportional. So that means one is a constant multiple of the other. So this second statement is establishing the equation. Rate is proportional to the size. And the size of the population would be the function, say, p of t, the population at a given time t. And the rate at which the population grows would be the derivative, because that's what derivatives tell us, rates of change. So if the size of a population is given by p of t, then the derivative p prime of t will be the rate at which that population is growing. And this statement is claiming that these two things are proportional. What that gives us is an equation involving a function and its derivatives. So we have an equation where the rate at which a population grows is proportional to the size of the population. And this is an equation involving a function and its derivatives.
Professor?
Uh-huh.
The K, that stands for proportional or rate?
Proportional.
Proportional. Is that like, so is it multiplying something, or is just, that's what it's just stating something?
That's just saying the rate is a constant multiple of the size. So K is a constant.
K is a constant. Okay.
So K is a constant. So what we're saying, when we say one thing is proportional to another, we're saying that those two things, one of those things is just a constant multiplied by the other one.
Okay.
So that's when things are proportional. So your gross pay is proportional to the number of hours that you worked. Because to calculate your gross pay, you just take a constant, your hourly wage, and multiply it by the number of hours you worked. The distance that you travel is proportional to the time spent traveling, because you just take the speed that you were going, that's the constant of proportionality, and multiply it by the amount of time that you were going, and that tells you the total distance. So those two things are proportional. So the distance is proportional to time. Gross pay is proportional to hours worked. And in this case, the rate at which a population grows is proportional. It's a constant multiple of the size of the population. One of the things that's being asserted here is that larger populations grow faster. So that's kind of the assertion that's being made. Larger populations grow faster. If we have twice as many members of the population, then the population will be growing twice as fast. Because there's more members to make more members of your population. Any questions? Clearly, this has to slow down at some point. At a certain point, competition for resources will be an issue. Space will become an issue as one population comes in contact with another population, and they decide in a very human fashion to just fight each other over perceived lack of resources. So, at a certain point, larger populations can't just grow faster forever because you just run out of space and things. Any questions? So we're using this, we're making an observation. We're saying the rate at which this population is growing should be proportional to the size of the population. And we're encoding that into a mathematical equation. The unknown, the solution to the equation, will be a function for the size of the population. So P of t is the unknown in this equation. Both mechanically and as an idea. So the idea is, I want to be able to describe what's going on with the population. And so I make this, I make this hypothesis about what's going on. I hypothesize that the rate at which a population grows is proportional to the size of the population. And that's the first step in encoding this mathematically, because we have observed that larger populations grow faster. And it's reasonable to think maybe if we have twice as many members, the population will be growing twice as fast. So it makes sense to encode this into some proportion. So P of t, we don't know what this function is doing. We don't know what this function specifically looks like, but this is a description of a function. That's an important thing to note with this differential equation. This is a description of the function P of t. This equation is a description of the function P of t. It's a description of the function P of t. So we're going to use this to try to inform us what P of t should look like. Any questions? Right. Let's pause the video here and talk about some other examples of differential equations.